Welcome back to the last session. This is going to be the last talk of this workshop, and it's been a long workshop going over 2 weeks, and I'm sure all of you have enjoyed it. I think we should take this opportunity to really acknowledge the people who made it possible. There were, of course, the academic organizers, of whom I was perhaps I deserve the least credit, and then there's Jaroslav, who did a lot of work, and Johannes, who did a lot of work. But apart from the academic organizers, the staff at ICTS really worked hard to make this program possible so that all of you could come. And there are many teams that work to make everything work seamlessly. There's the AV team that has been organizing things and making sure that the camera works, the recordings work, the audio works. There's a security team, and also the guest house team, and also the program activities team that really must have coordinated with you over several weeks and months and has been working to make this happen. So we should really acknowledge them, because without them none of this would be possible. Thank you very much. It really, without this, without you, we couldn't have made any of this possible. And it's really for those of you who've organized programs, it's really very smooth and very easy to organize a program in ICTS, and that's really because of all of you. And so, thank you very much for helping us pull this off. Thank you. Thank you. Okay, so with that, we'll start the last academic session. Our last speaker is Prashanth, who's going to tell us about complete monotonicity and dual volumes.
Thank you. So, quick recap about what we saw yesterday. So we learned what a completely monotone function is. It's a very simple definition in terms of derivatives of the function at all points in some region. And then we saw some physics examples. We saw some examples of integrated objects, primarily in planar n equals 4, but also other objects like scalar Feynman integrals, which had this property. And it had this property in either the Euclidean region or inside the positive geometry. And this was a property which sort of transcended different loop orders. So in all the cases, we saw that basically the property was true, morally some object like this, inside the Euclidean region or inside the positive geometry. And then finally, we also saw a characterization of these functions for the positive orthant. So we have this integral representation which says a function is completely monotone on the positive orthant if and only if it's a Laplace transform of something with a positive measure. This was last time. So today the plan is to sort of connect with positive geometry, so to see how these things are related to volumes and things of that sort. So to do that, so to give you some more motivation about why we want to do that, we saw that we're looking at some integrated objects. Okay, schematically, let's represent it like this. We have some integrand, and these guys usually are identified with the canonical form of some positive geometry, some rational function. And these guys we claim are, let's say, volumes of some dual. Right? Now, a fundamental property of duals, as we'll discuss, is that if X is contained in Y, then when we take the duality, basically this inclusion is reversed. So anything I do to increase, let's say, the size of my object, say X, will reduce the size of its dual, and hence the volume will decrease. Okay? Meaning the canonical form will decrease. So this is very loosely telling me that first derivatives in some appropriately defined way are negative. Okay? And this complete monotonicity basically has that condition, and it has infinitely many other conditions which we don't understand how it comes from the geometry. At least it tells you that things are connected in some way. So we want to sort of really go to this volume picture and try to see if we can understand more fundamentally where these conditions come from. Okay, so to do this, basically we are going to have to go to projective space. So it turns out the right way to think about complete monotone functions is in projective space. Let's talk about let V be a finite dimensional vector space. So a subset C of V is called a cone. It satisfies the following condition. So lambda x is in the cone for all lambda positive whenever x is in the cone. Okay. So a simple example might be the positive real line. Right? So this is a cone, but something which is not an example would be, let's say, the unit interval. Okay, so now you can also define a dual cone. So this is an element of the dual vector space. Which has positive inner products with elements of my cone. Okay, and now what we really want to do is we want to define completely monotone function on a cone. Okay, so definition. Okay, so here the d's are directional derivatives, and the vi's are vectors in the cone. Okay, so that's the definition. Maybe we can look at an example to understand this precisely. So recall that yesterday we saw that minus log x the completely monotone function 0, 1. Okay, and I just told you that 0, 1 is not a cone. So what we are going to do is basically we're going to go to projective space. We add another coordinate, let's say z, and then I'm going to rewrite basically the unit interval like this. Okay, so I've scaled x by this parameter z. So in pictures, basically what I've done. So this orange thing is basically this unit interval. I've just taken a cone over the unit interval. Okay, now I can also define the dual cone. So we just demand that for every point in the cone, the inner product is positive. And this basically defines this region. And this is C star. Okay. Now, how do I understand the fact that this function is CM in this cone language? I told you we have to check for directional derivatives. So basically, I also promoted my function. So let's say f tilde. And the function now looks like log z over x. If z is 1, we go back to log minus log x, as you can see. So this cone is a polyhedral cone. And basically, it's spanned by two vectors, which are these two rays. Okay. So I have V1, which is 1, 0, V2, which is 1, 1. And any V is basically a positive linear combination of V1 and V2. Okay. Since I'm only taking directional derivatives, in this case, it's sufficient for me to check for directional derivatives where all these vectors are either V1 or V2. Okay. And the directional derivative, let's say across V1 is going to be the dot product of the vector with the gradient of this function. The gradient of the function is basically this guy, minus 1 over x, because this I can write as log z minus log x. So negative gradient, which is what I have to check for the property, is just 1 over x, which is positive. I can check over V2. And this is again positive because recall that in my cone I had x is less than z, so this implies 1 over z is less than 1 over x. Right? things work. You can also check for combinations. I think you can trivially show that regardless of what directional derivative you take, all of them are going to be positive. So any questions about the definition or how we are taking directional derivatives? Okay. Yeah, so good. So what I'm doing is basically, so I take a generic point in C, okay, and I want to take dot product with, let's say, YW. So I'm taking XY, XZ, which obey this condition. I'm dotting with some generic YW, and I want to find all YW such that this is always positive, okay? So again, because I told you it's sort of polyhedral, so it's enough for me to do this only for these two extremal ways. When I do that, so I have YW dot 10 is positive, that tells me Y is positive, and then 11 tells me Y plus W is positive. Okay, sort of second more trivial example is when the cone is just a positive orthant. And in this case, it turns out you can check that this is actually self-dual. Okay, so the dual cone is actually equal to C. And here the extremal rays are just the unit vectors in all my n directions. And you can see that the directional derivatives just reduce to ordinary derivatives. Okay. Okay, so a slightly more non-trivial example, which will be relevant for when we go to positive geometries, is the case where we have this function. Okay, so just 1 over the equation of the circle. So you can see the connection to positive geometry because we know we have rational forms, and this would basically be what you would call the canonical rational function of those rational forms. If I want to connect CM to positive geometries, I have to study objects of this kind. Okay, so we have a circle, and again, this is basically just defined. So here the C, I mean here the region is basically defined by x squared plus y squared is less than 1. And this is also not invariant under scaling, so it's not a cone. Okay, so I take a cone over it. Okay, something of that kind. So I define a C in P2. Which basically satisfies the conditions. Okay, so in this case, finding the dual is a bit more complicated. So I'll explain how to find the dual a bit later, but take my word for it that C star is actually C. So this is also a case where it's self-dual. And this particular case is not a polyhedral cone. Okay, so there's no finite set of vectors which basically spans the whole thing. Okay, but generically I can sort of parameterize them and look at them. So I will look at Okay, something of that kind. And I can take directional derivatives along this guy. So by doing this, I also get an F star. This you can check just this function, which is manifestly positive because R is less than Z. Okay, and it's clear that if I can take several vectors with different R's, I call them Ri, and then these sort of directional derivatives are going to give me product of factors of this kind. So this function, which naively, I mean, if I had just an ordinary derivatives, I would never have thought of as Cm. Now has become Cm because we have gone to projective space. So that's the utility of basically doing all this. Okay, so what is the analog of the integral representation that we had for the positive orthant? This goes by the name of showcase theorem. Okay, it says okay, so it's just a generalization to the cone, but I mean, crucially, you have C star here instead of C. And because the positive orthant was self-dual, it looked like a Laplace transform, but that was just a coincidence. Generically, we are going to have different spaces. The second thing is that we get a stronger statement. It says not only is this mu positive, but it's supported only on C star. Okay. In other words, it's zero. I look at any point outside. So any questions about this before I want to talk about some applications, the result. Yeah, is the result clear? Okay, good. So already at the level of basically this representation, we see some hints of volumes, right? So we have a positive measure, we are integrating over some particular space, right? So these can be thought of as volumes in some very loose sense, right? Because the measure is positive. That's the crucial input here. So we'll see later that, I mean, the measure that appears in the context of positive geometries, at least for polytopes, is actually exactly in this form, with this mu being 1. And the broader question one would like to ask is, when you have non-polytopes, does this help you find a measure in some way to also interpret those as volumes? And that's the goal. Basically, we're going to see one toy example where this works out. Okay, but the theorem itself is very powerful, and it also gives you some non-trivial consequences. So the first consequence is convexity. Okay. So let's say F is Cm on C, and then we pick endpoints in C. Okay. Then the result is that the following combination is always positive. Okay, so the function obeys the property, and I'm just picking n random points in the space, and basically some inequality of this kind holds. Okay, and this sort of is closely related to the fact that these functions are convex. Okay. So for instance, if you had a function of one variable, you would interpret convexity as, you look at what is called the epigraph of the function. So you look at the part above the graph of the function, you take two random points, you draw a line through them, and this line always lies above the curve, right? So very simply, I mean, suppose I chose some generic points x1 and x2, then I would say something like something of that kind. And this is a generalization of, you can think of this as some sort of generalization of that for multivariate functions on some space which is a cone. Okay, so how do we know this is true? This is not really a proof, I'm just outlining how this comes about. So, like I said, the integral representation is basically crucial. That's where it comes from. So we can look at okay. So exponential e to the minus x of anything is less than 1 as long as x is positive. So we are just using that. So this combination is positive. But if you expand this out, you're basically going to see that this gives you exactly whatever I've written here, with f replaced by exponential xi. This gives you a star okay, and then we can just multiply by a positive thing and then integrate over C star, okay, because these are inner products between y and xi, and it's an element in C star, these are all positive, okay, and then that basically gives you that result. Okay, so this was one application. Sort of second, more non-trivial application. So these gave us some sort of linear conditions on f, right? So if I have a generic function, if I have generic ansatz with some coefficients, this gives me some sort of linear constraint on those coefficients. Now there is also a version of this where I would get some non-linear condition on the coefficients. some sort of Hankel determinant positivity. Okay, so for this, what I do is I choose a set of vectors. Let's say I choose generic vectors in my cone. And then I'm basically looking at this particular matrix. Okay, so it's a Hankel matrix because Aij depends only on I plus j. It's just a name. So now what I want to do is I consider some completely generic real vector. And then I basically look at xi transpose this matrix xi. Now using the integral representation, basically you can argue that this is always positive. Okay, so I have a quadratic form in n variables, which is always positive. Okay, so this only happens if this matrix is positive semi-definite. So this would tell me A is positive semi-definite, and one sort of condition for positive semi-definiteness is all the principal minors vanish. So if I write out this matrix, then all the principal determinants are positive. Okay, so that gives you a nonlinear condition. So just two sample applications. So if you're familiar with the story of the ICTS-Tehedron, you realize that the ICTS-Tehedron also arose because of these sort of similar conditions. Okay, so this potentially points to numerical applications in case you, yeah, that's what I want to highlight. Okay, so now we're going to move on. I'm going to talk about, I told you for the case of the circle that computing C star was not straightforward. I'll introduce the notion of dual. So let's start with something simple. Let's start with a plane curve. Now for a plane curve like this, you basically have a dual curve, which basically lives in the space of tangent lines to the curve. Okay, so I have a dual curve. And this lives in space of lines. Okay, so how is this connected? So I have to give you a proper definition. So this is just some statement. I have to give you conditions which would help me, for example, write down an equation for this curve. That's the idea. So clearly one of the conditions is the conditions that went into defining C star, right? So we had a condition which said C star is a set of all points vector space such that net product of y with x is positive for all x and c. Okay, but this, remember this was a condition in projective space. And generally the curve that we have might not be homogeneous. Okay. So this condition basically can be translated to the following. So if I look at all lines, satisfy this condition, and the way this comes out, the way we get this condition, is that I'm going to projective space. I have x, y, and a third coordinate, so I'm in P2. A third coordinate, which I can call, let's say, -1. And then I dot this with uv -1, and I want this to be positive. That you can check is precisely this condition. So we have ux plus vy greater than or equal to 1. This is one condition. The other condition, remember, is that they're all tangential to my curve. Okay, so I have some condition which says u is lambda times del f by del x, v is lambda times del f by del y. Okay, so there's a tangential condition. And there's a condition that comes from, there's a definition. Okay, so a combination of these. So so the procedure now is that I have f, let's say this is 0, and then I have ux plus vy equals 1. Okay, so I have all these equations, and what I have to do is I have to eliminate x, y, lambda to basically get some. Okay, so that is the procedure. Let's look at an example. I mean, the circle basically. Del f by del x, so it's going to be lambda x. And these imply, basically I can eliminate x and y. Plug it back into the other two equations, and that gives me and the only way these two are consistent, if 4 lambda squared is 2 lambda, this, if you want lambda to be non-zero, gives you lambda is half. Okay. So I have a GUV, which is just u squared plus v squared minus 1. Okay. So it's self-dual, basically. We got the same curve in the dual variables. Now you can do this for other cases. I mean, you can do this for more complicated cases, like if xy was cube instead of square, then you get something which looks not so simple. You get a degree 6 curve. Okay, so this is homework. You can just follow the same procedure and you should end up with this. Okay, and this generalizes. You can also do this for surfaces. So in this case, I told you that the dual basically lived in the space of tangential lines. If you go to higher dimensions, it's going to be some tangential hypersurface. You would get more conditions, but the procedure is the same. And you can find the dual like this in general. I mean, for each Fi, you'll get a GI, right?
And it's the same, so it becomes a system. I mean, is it the same?
Well, yeah, that's it should not be the same UV, right? Because you're putting a tangential condition. I mean, this tangential condition depends on what the curve is, right? If I change I, it's a different curve for which you're calling it UV, where you should not be calling it UV, right? You should be calling it UIVI or something. Yeah, but I mean, other thing you can do is you can multiply all of those equations together. You get some humongous thing, product over Fi, which is 0. You can find the dual for that. That could, in principle, have, I don't know, all your individual duals as some boundary components, if you like, but I think it's a very redundant way of doing it. Okay, so now let's sort of quickly go back to positive geometries. So I'm going to quickly define what a positive geometry is. I think nobody defined it except Jonah in the short talk yesterday. Not super important, but I mean, I think it'll be useful for making things precise. So it's a pair. So let's say, okay, so let me first define, we can define what is called a semi-algebraic set. And this is basically a finite union of equations and inequalities in projective space. Okay, and the other sort of ingredient we need is sort of a residue operation. Let's say I have a meromorphic form omega. And let's say this is associated to some variety x. And C is some subvariety of x. which is carved out by, let's say, z equal to 0. Okay. Then basically I can always expand my meromorphic form. Like that. And then basically this residue is defined as otherwise it's just 0. Some polynomial equations, let's say homogeneous. Okay, so you can take any polynomial in n variables, homogeneous, and I'm looking at equations and inequalities. Okay, so anything which is just a finite union of things like this is called a semi-algebraic set. Okay, so with these we can define definition. Okay, so it's a pair, let's say in of dimension d, capital D, satisfying the following. So D is 0, then it's just a point. And omega can be defined as plus or minus 1. And for D bigger than 0, you look at boundary components of X. And every such boundary component is a positive geometry. Of dimension d minus 1. And lastly, you have a third condition which says there exists a unique rational form a rational D form we're going to denote it by omega x greater than 0. It satisfies we take residue on the boundary component C. Okay, it satisfies that condition. So basically a positive geometry is something that has boundaries of all codimensions because of the second condition. And on each of those basically boundaries, and it has a unique sort of differential form associated with it. And when I restrict to each of these boundary components, the form also restricts to the differential form associated with that boundary component. Okay, so that's the definition. So generic examples, I mean, we've seen many examples, like polytopes in general. Fine. So what would not be fine is something like just the circle, right? So this cannot be a positive geometry because it has no zero-dimensional components. Okay? So it has no visual points. Okay, so just to write down some examples of canonical forms. So let's take one-dimensional real projective space, and let's say the semi-algebraic set basically defined like that. Then omega, we call it AB, interval AB. So you can check this is the unique rational form which would have residues plus minus 1 on each boundary component. It sort of uniquely comes about. There's an issue of orientation which would tell you, I mean, it could have been overall plus minus in front and so on, but yeah, we're not going to discuss that in detail. Yeah, so a second example would be, you take a triangle. Then to write down this canonical form, you would, so it's a 2 form, which would have boundaries defined by those inequalities. So I can put all of them in the denominator. And I can put some generic numerator, and now if I take residues at each of the boundaries, I'm just writing down some residues here. This would give you and fix the numerator. Okay, so generic strategy, right? You're given some positive geometry. You want to write down a canonical form. You would do some sophisticated version of this. So what you would do is you would put all the boundary components. Let's say you could put all the equalities in the denominator. Then what I would do is basically I put some numerator which now would have, let's say, degree of Q . Okay. So this is just to ensure that, I mean, the whole thing is projective and has projective weight minus m minus 1. For later purposes, basically, this function without this potential is what is called a canonical rational function. So now, for example, if you have some object that is defined by a conic and two lines, basically I'm cutting out a circle. Yeah, okay. Okay, so you can follow this strategy, and then you would get okay, if you took residues repeatedly. Now the nice thing about, okay, so nice thing about the numerator, so we have a numerator, we found the Q by repeatedly taking residues. So in certain cases, this Q has a very nice interpretation in terms of the adjoint that Shruti also talked about. So in this particular case, this 1 minus y actually turns out to be the line that basically cuts. So that kind. Okay, so I will not go through everything, but very broadly, I mean, there are various strategies for finding omega. I outlined one of them. You have other things, triangulations. Direct products. You have push forwards. And then you have what are called integral representations. Okay, and we are going to care about only this 4. So what is this representation? So let's look at simple example. Let's take a convex polytope. And a point inside. Then basically the canonical rational function of this convex polytope at y is basically given by the following integral. Okay, so this was, I mean, there are ways of seeing this. This was also basically given in the Arkani-Hamed, Pai and Lam paper of 2017. But mathematicians have known about this much before. In fact, I mean, if I give you a generic convex polytope which is cut out by inequalities, and I would want an efficient algorithm to just compute the volume of the polytope directly from these inequalities. Lasserre and Veron, I think, had a formula which is very similar to this, if I'm not wrong. And it's supposed to be very efficient. Okay, so this is how we would do it. And these people basically made the connection in the context of positive geometries, basically gave this formula. So here basically the measure, the thing to notice is the measure, because it has to be projective, so it has to be invariant under any such scaling that I do. And you can see that that is what fixes basically this power to be n plus 1. So apart from having a projective measure, I've done literally nothing. I've just integrated over basically the dual of the polytope. So this is just volume of the dual. Okay. So now to sort of connect up with complete monotonicity, we are going to have to rewrite basically that formula a bit more. So I'll write that formula again. We have okay, so you can, it turns out you can write this formula is also the same as okay. So here A bar means I've taken the cone over this dual polytope A. The way you would see this, I mean, the way you would see the two are equivalent is, let's say from here, I scale W. Okay. W hat, and I have a row. And let's say this W hat is now a unit vector. Okay, so I made it norm 1. And this row is positive. Now I can see that I rewrite this measure. So basically, if I do this, then the measure would just go to okay, so I'm making some transformation, it's some scaling, so there's a Jacobian, and that Jacobian just looks like that, let's say. So then I would get, so basically if I substitute back, I'm going to get something that looks like okay. Now I can just perform the integral over the row, and you can check that this just brings down a factor of W hat dot y to the power m plus 1, and then I can scale it back. I can make it okay, so these two formulas are equivalent. And this formula is sort of what is really important for us. It's clear why this is important, because this is exactly in the form of the showcase theorem for completely monotone functions that we saw earlier, but with measure 1, right? This is okay. So every polytope, every convex polytope is closely related to complete monotonicity in this sense. Okay, so I can take generic points inside the polytope, I can take directional derivatives. They're all going to be positive. That's what it means. Okay, so and in this case, basically the fact that a dual polytope exists gives me the property in some sense, right? Because this is a representation of the canonical form as some integral over the dual. And it automatically comes with measure 1. So the existence of the dual basically implies the property here. That's the thing to highlight. So just an example, I mean, in case you're not familiar with doing algebra of this kind. So let's take basically the interval and see that this Laplace representation basically reproduces my canonical form. Let me take this with vertices. So one of the vertices is origin, the other guy is at x. So I can compute the star at some, let's say, yeah, let me be precise. So if I write this out, I'm going to get the W0 is unconstrained, so I just get integral from 0 to infinity. W1 would go from minus W0 over x to infinity. And this, if I integrate, okay, so now, I mean, I just choose y0 to be 1, y1 to be y, and you get the familiar form. So you get 1 over y plus 1 over x minus y. And this I can slightly rewrite as this you would recognize as just the canonical rational function for the interval. Yeah. Yeah, sorry, we write it in the middle. This was basically this integral characterization of completely monotone functions. So this analog of this Laplace transform, but on generic cones. Okay, so it's just a Laplace transform, but the Laplace transform is defined on the dual. Okay, and the measure has to be positive. So comparing with whatever we got for convex polytopes, we have exactly this, but the measure is 1. Mu is 1. Okay, so that's why it's a special case. Okay, so now, I mean, the natural question to ask is what happens when you go beyond polytopes, right? Said everything for polytopes. So in that 2017 paper, so they did the following exercise. So they took, for example, that pizza that we just talked about. Yeah.
So just to orient, so like if apply to the association,
Mm-hmm.
that's a common formula.
Yes.
And so you can write this integral association.
Yeah.
So you're saying something like that. The tree-level amplitude for this right to this.
Exactly, inside the Associahedron.
And for loops, can you say something similar?
For, I guess, for all cases where the integrand comes from a positive geometry, which is a polytope, right? Everything I said goes through. So for example, all these surfaceahedra, right? They're loop level things, but they're all polytopes.
So, right. And so then you're saying the integrated result is
Yeah, so there is a big question here in the sense that, yeah, exactly. The integrated result is C. Sorry, no. So let me correct myself. So we have an integrand, which is a canonical form of one of these polytopes. And that canonical form basically has this representation. So the integrand is CM. Okay. Now in some cases, as we have seen, this also translated to integrated objects. But this mechanism is completely unclear. Okay. So for example, like Jaroslav mentioned, you write down this integrand in one space, and then you're doing an integration over Minkowski space. Now there is no reason for you to expect that the integrated result has any positivity properties, right? So the fact that this happens in certain cases is conjectured to be some sort of non-trivial property of the Minkowski contour. Okay. In general, what you would want to do is you would want to find some sort of, if it holds, right? If it holds, then you know that the integrated result would also have some Laplace representation like this, by Choquet. Okay. And what you would really need to do is find a contour deformation from your Minkowski contour to this contour. Okay. And nobody has any idea how to do this, as far as I know. Okay, good. So the last 4 minutes, I'm going to tell you about what happens beyond polytopes. So in this paper, they basically did the following interesting exercise. They took the canonical rational function of this guy, which we wrote down there, and then they tried to sort of perform this integral with measure 1, okay, where the C star is basically something you can compute. I told you how to find the dual, so you have these equations, you can find the dual of this beta slice. Yeah, so let's say you do that, and then you perform this integral, okay? So you have this, so basically I'm going to do, the following slightly different exercise. I'm going to look at the dual cone of the pizza slice, and I'm going to integrate this with the projective measure. Okay. And say you do this exercise, they found something really interesting. They found that what you actually get is basically the canonical rational function of the pizza slice, which is what you want. But then you get some transcendental part. You get things which are not rational anymore, you get logs. Okay? So what this seems to suggest is that, I mean, measure is not one, right? If your notion of dual is correct, then the measure cannot be one. If the measure is one, you don't get the right result. So you have to modify the measure. Okay? So now question is, how do you do it? Right? Does this property help you, for example, identify mu? Okay? This is work in progress, but I'm going to do this for a very little toy example. Okay, so I'm going to do this. I'm going to do a bit of cheating. I'm going to do this for an example which is not actually a positive geometry. Okay, which is the circle. The idea here is that basically, is just a toy example. I mean, to tell you how the procedure works. In general, you could also apply similar things to deal with problems like this. Okay, and the answer is basically, in this case, the answer is yes. It does help you find the measure. Okay, there is a procedure about how to find the measure, and this is a bit technical and it involves some calculation, which I don't want to get into now. So I'm going to just stick to this toy example. Okay, so what we want to do is basically we want to write this guy. This is, let's say, my disk. The equation is going to look like okay, so that's D, or D bar, should be precise, yeah. And basically I want to write this guy as an integral over D bar star, which is basically a dual of D bar. It's some measure that depends on VW. Okay, and I want to find this mu. So one key idea about how you would do this. So basically we want some analog of Schwinger, but for things which are not linear. Okay, that's where we are going with this. There's general procedure, but I mean one of the key ideas is basically this thing called Wishart distribution. Okay, so this is basically a probability distribution on the space of symmetric matrices. And any positive symmetric, positive semi-definite matrix by M, I call A. So this is a probability distribution, so something has to integrate to 1. Okay, I have 1, and this 1 can be written as some integral over the space of positive semi-definite matrices, B, which I denote by B greater than 0, dB okay, and there's some overall normalization, which is not important here. Okay, so this is a probability distribution. And the connection to whatever we want to do becomes apparent when I tell you that if A is this 2 by 2 matrix. Then you can check that determinant A is just the equation of the circle. Okay, so I managed to rewrite the equation of the circle as determinant of a matrix with linear entries. Okay. Now what I can do is that I can try to use this formula. So I have a generic matrix B, generic positive semi-definite matrix B. So I have A, B, we call it. Okay, and positive semi-definiteness of B basically tells me that A is positive, C is positive, E squared minus AC is positive. And if I compute trace of AB, I get the following. Okay, so now I started with something that had 3 variables, x, y, z, and I want to identify some dual, u, v, w, and I'm integrating over a space of matrices which have 3 parameters, ABC. Okay, so in this case, the parameters exactly match, and all I have to do is basically think of this as some ux plus dy plus z. Just take 2 minutes. And if I actually solve for UVW, so we have, remember, if I solve for UVW, I'm going to get, together with A positive, C positive, B squared minus AC positive, then you'd see that you basically get this guy. Which is actually exactly the dual cone of my circle. This is not a coincidence. There's a reason why it works, but yeah, we want to get into it. So you can use this, and then you end up with this formula up to some overall number. Okay, so we managed to write it as some sort of an integral where clearly the measure is positive, because the measure represents the equation of the dual. Okay, and there are some details, but the whole point is that for cases where I can write the denominator as a matrix of a symmetric determinant, this procedure works. Okay, and this has been proved by mathematicians. So cases where I can write down the denominator as a determinant of a symmetric matrix are a subclass of what are called hyperbolic polynomials. And generically, mathematicians have studied complete monotonicity of negative powers of hyperbolic polynomials. And this is the procedure. I mean, to show that it's actually completely monotonic, this is what you have to do. For more complicated cases like the pizza, the parameters will not match. So I will have more. So I'm embedding basically something that is in n variables in Rn into something in the space of positive semi-definite matrices, which in general have m into m plus 1 by 2 parameters. So it's a much larger space. And I would have to really think about how I can integrate out these other directions. So that is the challenge. But the fact that if I eliminate things and I basically solve, I identify parameters of this kind, it will give me the equation of the dual. And then if I integrate out things, I recover the measure is a theorem. Okay. Practically speaking, it's a theorem, but if you want to practically apply it to cases we care about, you would have to figure out how to integrate out these directions. And this leads into the same sort of problems that Jaroslav was talking about. You have some inequalities, you have to resolve them. You have a bunch of regions, you have to do the integrals over all of those regions and then combine them. Okay, but in general, you can do it. Okay. Now, of course, the natural question is, does this apply to all positive geometries? Right? Can we write, for example, the denominator in all these cases as a symmetric determinant? The answer is no. There are, of course, cases where you cannot do it. Well, specifically for positive geometries, I don't know, but there are examples, like simple examples you can construct. Where definitely, the denominator is not in one of these classes. Okay, for those things, basically this procedure will not work. And we don't know how to address the problem there. Okay. But at least in these simple toy examples, it seems like this property does help you find the measure. Yeah, that's basically all that I want to say.
Thank you very much. Any questions?
Yeah, I wanted to ask, so these global Schwinger parametrization integrals that they've written down for like J5 cube, Nima et al.'s papers, that seems to look a lot like the showcase theorem.
At the level of Laplace transform it does, but there, the point is that things that appear in the exponent are some piecewise functions, right? So I don't think it's naturally this. I think you have to do something more to it before you actually put it in the showcase form. Yeah.
Do you expect that that's possible and you can show that all of the resulting, because that is genuinely a loop integral.
Yeah.
It's not an integrand. So in that case, do you think maybe you could show that all the resulting things are positive, like CM?
Maybe, I don't know. I don't want to speculate, but I guess it's something natural to try. Yeah, that's all I would say.
Thanks.
Just a broader question of if the complete monotonicity property that you talked about, how does it interplay with unitarity and analyticity of scattering amplitudes?
Yeah, so like yesterday I discussed some cases where we proved it using some sort of dispersion or Mandelstam representation. So in those cases, it seems like unitarity and locality in some non-trivial way imply these positivity properties. But generally in the context of positive geometries, it seems like it's more general, right? Because in positive geometries, we generally think about unitarity and locality also emerging from the geometry rather than being some sort of inputs, right? So there, everything you would ask should naturally be connected to the geometry rather than those things. Philosophically speaking,
But from the dispersion relations, you're saying there are
yes,
some examples that are known? Or
in fact, some of these results were known in the 80s. So Andre Martin, so he has a book in which he has a particular case where he's looking at pion, generally pi 0 going to pi 0 scattering, and you have a dispersion relation. in that case, which is some sort of a two-channel. So you're looking at something that's oral speaking. Yeah, orally speaking. This. Okay, so some two-channel, some twice subtracted two-channel dispersion of that kind. So from this representation, by doing some simple change of variable, you can actually show that this is positive for fixed t in this range. Okay, and there is a similar sort of statement about derivatives in t and u. Okay, and this you would recognize basically we normalize things differently. So our Euclidean region is when s is negative. So if you make the change of variable where you take st and u to minus s minus t and minus u, this is exactly complete monotonicity. Okay, in fact, in particular, what this would imply is that, let's say I'm looking at the Mandelstam triangle. Let's say it's equal mass. Let's say all the masses are equal. And basically, I have a Mandelstam triangle, which would be the analog of the Euclidean region, or so to speak. That's the region where the amplitude is real and analytic. There's a crossing symmetric point here, which is 4m squared by 3. This is s direction. So this is s is 4m squared. This would be t direction, let's say. So that's t equal to 4m squared. And this is u equals 4m squared. Now what that would tell you, because I told you that complete monotonicity means that things would decrease inside the region. What that would tell you is that if I draw any line here of this kind, then the value at this point, any point on this line, is going to be smaller than the value at any point on this line. Okay, because it's the s direction and things have to decrease along the s direction. So basically, whatever your amplitude is, it can be a complicated object. It has an absolute minimum at the crossing symmetric point. If you interpolate this all the way back to the crossing symmetric point, that's what it implies. And Martin in his book, he basically says, we don't understand why these things exist, but they have merit to exist, because you can mathematically prove that it works, right? Then he tries to use it to, I don't know, constrain some things about partial waves of pi 0, and so on. He does some numerics with it, basically.
Maybe I can ask, does your constraints, can you hope to be able to bootstrap amplitudes or something like that using?
Yeah, this is actually work in progress. So we are trying to sort of, this is work in progress with Sarah, who's a PhD student in Munich, and Johannes. So we are trying to numerically bootstrap Feynman integrals from the differential equation. What we have is basically we have a canonical differential equation. Now what you want to do is, from things I argued last time, so scalar Feynman integrals in general in the Euclidean region are completely monotone. And by using my IBPs, I can always choose a basis for my differential equation, which is Cm. Okay. Now I've chosen this basis, I have a differential equation. Now, this differential equation allows me to write higher derivatives of my basis in terms of basis and derivatives of my matrix, right? So I have sort of linear constraints demanding that it's CM because the basis is CM, demanding that they're all positive. I have a set of linear constraints on these basis elements. And the question is, can you sort of choose a kinematic point and numerically bootstrap this basis? So that seems to work quite successfully in a lot of cases. We don't exactly understand the mechanism of why it works. Seems like it works very efficiently. Yeah. So the short answer is yes.
The other questions? Last questions to end the program. Okay, so if not, we'll thank the speaker again. So